In this video, we'll find probabilities for a random variable x that is a binomial random variable. So remember that a binomial random variable x is one with the following property, where x is the number of successes in n trials, where the probability of success in one trial is p. An example would be this below. Suppose 60% of registered voters in Berkshire County are Democrats. If 12 voters are randomly selected, what is the probability that exactly 10 of them are Democrats? Okay, so this is binomial because there are 12 trials, so n equals 12 is the number of trials. We are looking for the probability of exactly 10 Democrats, so we're looking for x equals 10 Democrats, and we say that since Democrats is what we're looking for, success is an individual that we select being a Democrat, and p, the probability of success, is 0.6 because it says that 60% of registered voters in the county are Democrats. So how can we find this probability? One way is to use a binomial distribution table like the ones we see below. And so the ways these are set up is that n, the number of trials, is on the left-hand side. So this is 2 trials, 3 trials, 4 trials, and so on. And then within each of those, if we're looking for x, the number of successes, so for 2 trials, here's 0, 1, and 2 successes. And then the probability of success in one trial, there is p, the probability of success in one trial. So for us, in this example, we're looking at n equals 12. We're looking at a probability of success of 0.6, and we're looking for k, or for x, being equal to 10. So we would see where that row and that column match up. So here's the row we're interested in, and here's the column we're interested in, and so that matches up at 0.064. I'll do that again on a blown up version below. So again, we're at n equals 12. Up at the top, we've got 0.6 is the probability that we're interested in. So 0.6 was in this column, and so we're looking at blowing that up and looking at this row, this column. Where do they match? They match at 0.064. So the probability that x is 6, the probability that x is 10, that there are 10 Democrats out of the 12 voters we randomly select, is 0.064. So that is our binomial probability. Let's look at some more examples with this same premise. So the probability that x was exactly 10 we saw was 0.064. So what's the probability that at least 10 of them are Democrats and that 9 or fewer of them are Democrats? So we're still going to be looking at the same value for n equals 12. There are 12 trials. Again, that's the extreme left-hand side. And we are still looking in the same probability, p equals 0.6. You can't see that in this blown-up version, but this is that column. And so we're still interested in that section of the table because we still have the same p value, we still have the same value for p, and we still have the same value for n. And so what's the probability that at least 10 of them are Democrats? So the probability that x is greater than or equal to 10, well, that's the probability that x is equal to 10 plus the probability x equals 11 plus the probability that x is equal to 12. And so that would give us probability that x is 10 is 0.064, plus probability that x is 11 is 0.017, plus probability that x is 12 is 0.002, and I'm getting that by reading these values of the table for x equals 10, x equals 11, and x equals 12. And then I can just add those values together to get 0.083. So the probability that X, the number of Democrats in my random selection of 12 voters in Berkshire County, is at least 10, is 0.083, or about 8%. What's the probability that 9 or fewer are Democrats? Well, one option would be to add up all those numbers, and adding up all those numbers would give me the probability that 9 or fewer are Democrats. Another option is to use the complement. So the probability that X is less than or equal to 9 is equal to 1 minus the probability that X is greater than or equal to 10, because either 9 or fewer of them are Democrats or 10 or more of them are Democrats. And so that's 1 minus 0.083, and that gives me 0.917. So that is my probability. You can also use a binomial probability calculator. Some of your actual calculators that you may have at home have this ability, like if you look at usually the probability button, if your calculator has one. If not, you can also use online versions. So here is a website for an online binomial probability calculator. If you just Google search binomial probability calculator, you can easily find this one or similar ones. But for example, with this one, you enter the probability of success on a single trial, that's P. In our case, that was 0.6, 60%. You enter the number of trials, that's N, our number of trials. The number of successes for part A, the number of successes was 10 that we were interested in. And then it gives you a bunch of different values. So the first thing it gives you is just the probability that X is equal to that value. So we had 0.064, and you can see that that's what this would round up to. So this is a more precise version of that. You can find the cumulative probability, the probability that X is less than that. So this is the probability that X is less than 10. And so we did calculate that as well. The probability that X is less than 10 is the same as the probability that X is less than or equal to 9. We had calculated that as 0.917. So 0.917 was our calculation from the table. Again, note that this would round up to that value. This is more precise. Cumulative probability for X less than or equal to it. This is probability that X is less than or equal to 10, and basically it's just adding those two values together, and so on. So it's also giving the probability that X is strictly larger than 10, and the probability that X is greater than or equal to 10, which we calculated this as well, and that also conforms to what we had above. Again, this is just a rounded, we had 0.083, and if you round this, you will get the same result. All right, suppose 40% of people say that blue is their favorite color. If you have 10 friends and 7 of them say that blue is their favorite color, is this value unusually large? And when we say unusually large, what we mean by that is, does a value this extreme or more extreme occur less than 5% of the time? So if our value is like X right here, we aren't just interested in how often this particular value occurs, but by saying unusually large, we're saying what is the probability that X occurs or any other value that is at least as extreme as X. So we would be looking for the probability that X is greater than or equal to this value for considering whether a value is unusually large. So think about that problem. You can use the binomial probability table to the left, and we'll talk about it in a moment. Okay, so we are going to be using the value the value n equals 10. So we want n equal 10, and so that's the part of the table that we're going to be looking at. We also want p equals 0.4. So p equals 0.4, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We're going to be looking at p equals 0.4, 40%. And so does this value of 7, if 7 of your friends say that blue is their favorite color, is this unusually large? As we said, we want to look at the probability that x is equal to 7 or higher. We want to look at the probability of a value this extreme or more extreme. So the probability that x is greater than or equal to 7 is adding up those probabilities for x equals 7, x equals 8, x equals 9, and x equals 10. So 0.042 plus 0.011 plus 0.002 plus 0. So we've got 0.055, 0.055. This is greater than 0.05, this is greater than 5%. So because this value, a value this extreme or more extreme happens more than 5% of the time, we would say that no, this is not unusual by our definition in the course. All right, if you flip a coin 8 times, what is the probability of exactly 4 heads, 4 or more heads, and part 3, all 8 coin flips landing on tails? So you can use this binomial probability table to find that solution, and we'll talk about it in a moment. Okay, so we are flipping the coin 8 times. That means n is 8. We have a probability of success, heads, tails equally likely, so 0.5 is our probability of success. If we're looking for the probability of exactly 4 heads in the beginning, so we are going to be looking at the section n equals 8. So we're looking at this section of the table. And then we are looking at the probability of 0.5. We're looking at the probability of 0.5. So that is this column of the table. And we can blow that up. So this is n equals 8. And this is our p equals 0.5. So the probability of exactly 4 heads, here is n equals 4, and here is the probability that x equals 5. Those line up at 0.273. So probability that x equals 4, that there are 4 heads and 8 flips, is 0.273. So that is the most likely outcome. If we compare it to, all the other possible outcomes, we see that 0.273 is larger than everything else. But note that it is not like 50% chance that half of them are heads. It is 0.273 is the probability of 4 heads in 8 tosses. If we look at the probability of 4 or more heads, then that would be adding up all of these values, the value for probability that x equals 4, x equals 5, and so on, all the way up to x equals 8. So we can add those values up. It's 0.273 plus 0.219 plus 0.031 plus 0.004. And if we add those values up, then we'll get 0.636. So 0.636 is the probability that x is greater than or equal to 4. And finally, the probability of all 8 landing on tails. So the probability that all 8 land on tails, we had been considering x as the number of heads, so number of heads. So if we continue with that frame of mind, then we're looking for the probability that x is equal to 0. So the probability of no heads, that would be 0.004. Note that if we had done like the opposite, if we looked for a probability that x equals 8, we would have gotten the same thing because heads and tails are equally likely in this case. If we were looking at, a different, probability equals 0.2 or something like that, then these wouldn't be symmetric. We see that this and this are different values.